and the gas cost. Transaction cost, which is the execution plus the transaction cost. When you send a transaction into the blockchain, you're executing code. So even if it triggers some kind of functionality in another contract or a wallet, it's going to execute some operation code, some opcodes. Now in the blockchain, in Ethereum, every opcode consumes some amount of gas. And this is what the gas limit actually is. When we send a transaction, we set the amount of operations that we're going to perform or that we assume we're going to perform. Every contract is different, so the amount of code that's going to execute on the back, may vary. Now, the gas price is the amount of price we set to each unit of gas. If you multiply that, it is the kind of reward that the miner gets when they actually compute your transaction. When the miner consumes and operates, checks your transaction, they will start deducting from the gas limit you set the amount of gas that they actually took to perform this operation. The surplus that remains will be sent back to you in another later point in time. If the gas is not enough, the transaction will get reverted, meaning that you didn't give enough transaction fees for the operation to be processed. This is just for the concept of gas that we're going to need later to understand the vulnerabilities. A few things about transactions. When we send a transaction to another party, it is not written to the blockchain instantly. First, the transaction is added into a transaction pool. In this transaction pool, every unverified transaction is there. Now the miners will go into that pool and will start picking the transaction that they want to add it into their own block and publish it later into the blockchain. Now miners are a bit selfish and they want to choose the transactions that are more profitable for them. Also, the blocks that miners produce have a certain limit. They cannot add an infinite number of transactions. The average number of transactions within a block are around 100. So the miner will have to pick which transactions are more appropriate for that block at that time. This is why miners choose the more expensive transactions. This is why the gas price, we talked before, is important. The higher the gas price, the more probably you are to be selected, your transaction, to be selected by the miner. Now, let's move on to the first type of attacks. This is the attack is called front running, and it is very simple. It is, I'm going back to the previous slide. When an unverified transaction lies into the transaction pool, it is possible for other users of the blockchain to monitor that pool and try to find whether the transactions lie in there. So, this is very common in decentralized exchanges. So, the example I'm going to use is with traders. Let's say you're a successful trader and you know what you do. And you make a call, you're trying to trade buy a certain coin at a certain price, and you make the transaction. If someone knows your address and knows what you're actually going to do, they can monitor you. And where your transaction is in the transaction pool, they can actually see what you're trying to do and send the exact same transaction, but with higher gas price. Now, because miners are selfish, they're going to choose their transaction instead of yours. Or they could choose yours as well. But since it is more expensive, they're going to prioritize it with a higher priority in their block. So you can actually lose the position you have in the platform by someone who actually spends more money in a transaction. It is very easy to monitor a transaction pool. It's more like a script monitoring for a certain address to trigger a transaction. So it mostly affects smart contracts, which is a first in, first out type. The first who gets there gets the result, the reward. The second might not get the reward, or they might get the reward maybe deducted, or at a more expensive price. There are two different types of front running. It's the user front running, which is what we actually explained right now, and it is the miner front running. The miner, this is less probable to happen because miners are they can do this, but it's less probable to happen. It's when the miner actually crafts a block, and because they craft a block and they're in position of power, they can actually see what you're going to send, and they're going to place their own transaction on top of yours. So it's kind of the same thing, but the impact is much less because the miners are much less than the users of the blockchain. For examples, I have generalized exchanges, that's the DEX. Bancor is one decentralized exchange which actually was vulnerable to one user from mining. It is fixed. The reference for that issue is on the bottom. And this is a small piece of code. It's a very naive example of how front running could be triggered. Let's say that's a smart contract that gives away free Ethereum. That's 1,000 free Ethereum to the first person who actually calls that function. If I know that someone's going to trigger this function, or if I know that a certain contract is going to go live at some point, I can time that very quickly and send the transaction, get the Ethereum, and lock the other person out. Apart from decentralized exchanges and those kind of applications, front running can also happen in ICOs. Just as a small story, me and a friend of mine at some point were trying to invest into an ICO. It was just £200, but that's something. And we did all the signing up, we got the whitelisting, we were ready to send our Ethereum to their contract. The token sales started at 7 a.m. At 7 a.m. we had sent the transaction, but it failed. Now this is very weird. It's very weird and not weird at the same time, because in ICOs funds go away very, very quickly. And I started digging up with Etherscan to see the transactions that actually went through, what happened there. Most of the transactions were invalid, and apart from the first few transactions. So one of those transactions had an extremely high gas price. So that party actually bought the majority of the tokens of that token sale, but they had to pay the equivalent of 3,000 USD in transaction fees. So that was a very expensive transaction. The average transaction fee is 30 cents, something like that. But again, that was a way to outline everyone, put them on the back, and then getting all the tokens out of that token set. This is a screenshot from, it was a Twitter post, and the reference is on the bottom. This depicts what is the reordering, the pricing in an average block in the blockchain. This is the price of each transaction that they actually use, and on the 15th percentile, it's the lowest prices. The recommended price for a transaction in the blockchain is 60 GUI, which should be around here, right? On the 99th percentile, on the slot 0, which is the first transaction in the block, we see that the price exceeds the 500. That's 10 times the average price that someone pays for a transaction. So for every block, this is not very weird, this is very common. Important transactions have a lot of transaction fees because they need to get processed very fast. But sometimes they get to extreme lengths. So what can we do to mitigate from running? There are multiple ways to do that. Each case may vary, but a very quick and easy way is to control it from within the smart contract. We can set an upper gas limit, and we can set a fixed limit. Setting an upper gas limit is very common. A fixed one is very rare. I think I've only seen that once. You can do this with this variable and this function. The gas price actually reports to the contract what is the gas price that was used when conducting this transaction. And the gas left returns the amount of gas that is remaining for this operation. Now, since we said on the first slide that each operation, each opcode, when executing, they consume gas, the gas left will always return a different amount, a smaller amount. So it's very difficult to control that. But we can definitely set the gas price. This is a snippet of code which it can be used like that. And this is another approach. This is the commit review approach. Again, this mitigates from running. It is split in two different phases, the commit phase and the review phase. In the commit phase, we send our intention as a hash. We have our input, we perform a hashing function, and we provide the service with the output. So they know we have a time slot where we actually make an intention to do something. And at a later point, at the review phase, we send the input. So in that point, there is no way for someone monitoring the transaction pool or the network to identify that from the hash, what is our intention. Unless, of course, they break the hashing algorithm, which is a completely different problem. Now we're going to payable functions. Again, we're going with some basics of the blockchain of smart contracts. In payable functions, it is the verb that actually makes a smart contract able to receive funds. We can add the verb in both functions, and each smart contract can have one fallback payable function, which is the second one, on line 5. Now, on line 5, we can send funds and trigger this function if we just use the address of the smart contracts and send the funds, which is exactly the same thing that we would do if we were to send funds to an address. If we want to call the function, we need to use the address, the name of the function, and use the funds as well. We're going to need that in the next issue, which is re-entrancy. Re-entrancy is a very interesting issue. It is, I don't know if it's safe to say that it's what made security in smart contracts possible, but it happened with DAO. DAO is the decentralized autonomous organization of Ethereum. It was a project made to fund some different crypto projects. This smart contract had around 150 million in funds, and it had one vulnerability. This vulnerability caused them to lose all of their funds. And as a result, this caused the mayhem in the Ethereum community. Ethereum had to make a hard fork in their own blockchain, meaning they had to go back in the blocks, which is a very big violation for the blockchain, and had to switch and had to use a different history. Now, even this happened, and since they actually changed the actual blockchain, we can really say that those 150 million were actually stolen, because in that different history, they don't exist. But that's another story. As a fun fact, this fork actually caused Ethereum Classic to be born, and it is a community that actually continued that fork of the blockchain. Now, re-entrancy. What is this? It is a kind of vulnerability that actually exploits the lack of prioritization and excessive usage of gas. This is a very naive smart contract. This is vulnerable to re-entrancy, and it has two different functions. The first one is deposit. So we deposit funds, and we withdraw funds. If we go through the withdraw function, the first statement requires that the user has funds, so they can withdraw those funds. The second function, second line of code, line 7, goes and sends funds to that user, to the sender, and the last one actually deducts from that user what they actually took out. The issue here is that we make the deduction in the balances of the user after we make the send operation. And the first one is that we use a function which delegates too much gas to the next in the line. How can we attack this? It is very simple with this attack contract. So on below we have the attack contract, up top we have the vulnerable contract. The attack contract consists of two different functions, the attack and a fallback payable function. On the first function, the attack, what we do is we instantiate the victim contract. This is very easy to do if you have the source code of the victim and their address. So you make an instance of the contract, you deposit some funds, so you can bypass line 6 of withdraw function, and then you withdraw the funds. So what will actually happen in the code is that when we trigger the withdrawal, we'll go to withdrawal, pass line 6, because we do have funds, and this is a valid statement. We'll go to line 7, where we actually trigger sending the function that sends the funds to the sender. Now the sender is a contract, and as a contract, because we actually use the address and some funds, they will go directly to the payable function, which in turn will trigger the withdrawal function again. So now we have some kind of recursiveness. And this will go on and on and on till we set limits in our function. This is a very naive attack example. In reality, they would actually limit the amount of times they can go in this function. So let's say that they go 2 or 3 different times. It is possible to perform this one because on how the stack works, this line of code will never trigger, or it will trigger in a very later point in time. It will be too late. So calling withdraw, passing the first statement because we have funds, calling send funds, going back here. This does not trigger yet. This will trigger if this function allows that. I don't know if that's very clear. All right. Yes?
Yeah, I mean, I don't know anything about Ethereum, but in Bitcoin there is no loops, and this is a variation. Sorry. So as I understand it, the Bitcoin code, and that's the reference client for Ethereum, has no loops in the code. It's not possible to do a DDoS by like looping. So like Ethereum is a variation on it's nested inside the same blockchain, isn't it?
It's a different completed blockchain.
Different blockchain.
Yeah.
Okay.
Bitcoin is not Turing complete. Ethereum is Turing complete, and it allows for the code to do loops and more advanced stuff.
So as soon as they introduce the possibility of a loop, then there's problems. Okay, that's all I'm saying.
So this is the re-entrancy. Mitigations for this issue. Instead of using the transfer function that we're using right here, called value, there is a designated function that actually performs this operation, but in a safe manner. It is called a transfer. The transfer function will only delegate enough gas to the other contract that it can actually receive the funds, and they cannot perform any other operation. So even if the receiver contract had this kind of logic, it wouldn't even trigger, because there wasn't enough gas, the transaction would revert, and that would never happen. The second option that it's a very good advice to follow in every smart contract, always use important operations before trying and calling external contracts. If you call external contracts, you're never certain that it's going to happen. What is the intended behavior? The third option, if you need to use the call value function, or you're worried about having a re-entrancy issue at some point in the code, the re-entrancy guard is a mutex-like modifier that can be used, and it's basically a flag. Setting a flag before and after calling a function, so you ensure that it's called only and only once. The reference is for the source code of re-entrancy guard. And yes, let's go to the next step. Since there is a transfer function which is safe for re-entrancy purposes, even though we started seeing a lot of re-entrancy attacks at the beginning of 2017, by now they were obsolete. No one was using that. Everyone was using transfer, they were using safe operations that wouldn't allow for an attack to take place. But we also saw a different thing. In 2017, there were like 1,000 different ICOs, different tokens being developed every single day. The majority of them were ERC20 tokens, which means they were operating on top of the Ethereum platform. Now, the thing is that many different organizations try to bridge different blockchains. For example, the way to actually send Ethereum from Ethereum to Bitcoin and Bitcoin to Ethereum, but in a native way, which is not possible yet. What is possible is to connect different ERC20 tokens, because it's in the same language, in the same prototype. It's much more easier to do that. Those kind of applications, we tend to call them bridges. They bridge two different tokens, and they allow the safe transaction in between them. Now, this is the new kind of re-entrancy that we basically see the last few months. There are applications which try to make a generic approach to different ERC20 tokens. For example, have a token which accepts and makes use of two different tokens. Again, a very naive example. We have a contract with a different project in the blockchain, and they want to operate like a gift card. So if you use their own contracts with their own tokens, you can transfer any other ERC20 token from within their platform. And as a reward, they're going to give you something back. So they're going to mint some tokens. Now, the issue here is that this function trusts that an ERC20 token is going to be an ERC20 token. In reality, this is just an address. This is just a type of variable, and they're trusting that this address is going to be a token. And they behave like that because they use the transfer function, which is, again, by the prototype, it's being used, and it's normal. The thing is, I can make contracts which can be interpreted as an ERC20 token. And I can have a transfer function inside, but it will do different things. And in this example, what I'm doing is, when they call the transfer function, I'm calling back the gift function. What I'm trying to exploit at this point is to trigger the mint function to get the reward multiple times without me spending a dime. Now you're going to think that this is not a re-entrancy per se. You're trusting a very unknown object and you're putting too much trust on that. And that is true. The re-entrancy right here is the impacts and not the issue itself. It's more like a call to the unknown, which is the next topic. It is very common to have the need to use external contracts into your own code, into your own projects. And in traditional programming, this is very normal. We do this every day. We have libraries, we have everything. But in smart contracts, it's different. You might have some functionality that requires that you send and make use of different contracts, as we saw before. In this case, we do either of two things. First, we trust that the function we're calling, we know what it's going to do. In the previous example, we believed that if that function was triggered successfully, it would have as an input an ERC20 token, which was wrong. The other option is that the function that we're calling is going to succeed. This is the example we see here in the code. Now, this is the method sender send is an internal functionality. It's on an external contract, but the concept is the same. There's a small difference. You can send funds with many different ways. But the two most basic ways is send and transfer. Transfer is the safe way, because if the function fails, it is going to revert the transaction. And send will fail silently, meaning it's going to return a false Boolean variable. It's not going to revert anything. So in this case, we're using a destroy function. Let's assume that this can only be used once. And this contains a very big amount of funds. It's 100 Ethereum, 1000 Ethereum. And when we use this function, it does not have sufficient gas to make the transaction, the send transaction. It fails. Since we don't check what is the result of the function, it can lead to the next step, activating the Boolean destroy, and we won't have access to this function again. This is lack of checking what is the result of the external functionality. Mitigation for these issues is mitigation. You should always be cautious when calling external contracts. You should always perform safe operations that could cause harm to your own contract at the beginning of the function. You shouldn't do them after calling an external contract. Yeah, very basic. Never assume functionality. If you're trusting something blindly, it's going to go wrong. Now, integer overflows. There are two basic cases where integer overflows actually happened and caused an issue. The first one is proof of weak hands token coin. It was a Ponzi scheme in the blockchain, and there are too many of them in the blockchain. And that caused 866 Ethereum in losses. The next occurrence is the batch overflow. That was a piece of code that was added in at least 10 different tokens. They weren't very highly profiled tokens, even though some of them were listed in exchanges. So this piece of code had a fault inside one of their functions, and during a multiplication, which wasn't performed safely, it could cause an overflow. And as a result, this is the amount of tokens that were extracted from the contract. It has too many digits, and it wasn't good for them. There are around 20 different types of how an overflow can be conducted in smart contracts, in Solidity. And meaning that it can be performed with addition, division, subtraction, using the plus, and what I prefer the most is conversions. And this is something that I see very often in audits for smart contracts. It's converting unsigned integers to signed integers. Now, as you know, integers, unsigned and signed integers, they can overflow if you cast them to the other party. And one time I was very close into getting a very critical one, but at the last step they had an upper limit, and someone found it before me. So mitigation, again. You should always perform operations within boundaries. You should always perform operations safely. There are safe libraries out there, like SafeMath by OpenZeppelin, I think it is. Yeah. And they replace the common addition, subtraction, division in order to make them more safe. If you use those functions, you cannot extend the limit of the integers and cannot cause an overflow or underflow. If, again, you need to be certain that you won't go over certain limits, that's an advice that I provide, is to actually set the limits, the bounds that you don't want to exceed. And this is TX origin. This is the equivalent of the blockchain CSRF. TX origin is, this vulnerability is caused by the mistrust of the contract that TX origin is the same as the message sender. Now, when I send a transaction, it does have an origin. And this is the first person, the first entity that triggered that transaction. In contrast, the message sender is the latest in line that called the final contract. So this is a very common function. This is a vulnerable function. Here the trust that the TX origin is the same as message sender. So if a user calls this function, first they're going to check that the TX origin is the same as the owner of the contract. And if it passes this check, they will transfer the funds to their own wallet. This is how it actually translates for the end contracts. We do have the user and the vulnerable contract, so if I directly call the contract, for the contract, I'm going to be both TX origin and message sender. But if I add an intermediate, a delegator, who will delegate this functionality to the final contract, this will be different. Because for the end contract, the TX origin will be me. It will be the one who initiates the transaction, but the message sender is the intermediate. And in that case, we'll pass the first check, who is the origin of the transaction, which is the first entity, and the second one, who did the transfer, who to send the funds to, which is going to go to the malicious contract. Now, there's a possibility to bypass that and make from the code, perform from the code. If you use the delegate call function, the malicious contract can, if they want to, delegate the user, the TX origin, and make it as a message sender. Does it make sense? Perfect. TX origin can be used. It's, in some cases, it is vital for the contracts and the business logic to use the TX origin, and we've seen it in use. And when you use that, you should always be cautious. You should always check all the possibilities that someone can misuse that. Again, if you're not certain that you need TX origin, just put it out. Just use message sender, and it's going to work. The next type of attack is the gas limit. The gas limit attack is what happens when you loop over arrays of unknown length. It is possible to exhaust the gas of a transaction and not being able to predict it if you don't know what kind of array you're looking through. So in the case, that's the most common example is for token sales, where they actually try to distribute the funds, so they go over all of the whitelisted investors. This could be thousands, maybe hundreds of thousands of users. In those cases, the length is very, very big, And if you have too many transactions inside, it's going to consume a lot of gas. This can lead in denial of services or in very expensive operations. Could be just to loop over all the array, it might cost from a few cents to a few $1,000s each time. So if you don't know the exact length of the array, you should either set an upper limit, or you can actually check from within the function, the iteration, if you have enough gas limits to complete all of the opcodes. In this case, when we perform the loop, we actually check what is the left gas, and if it's enough to perform the transactions inside this loop. If not, they just end the operation and the transaction will not revert. I don't know if I went too fast, because I felt it went too fast. It went too fast, right? How much time do I have? 5 minutes. Okay, that's perfect. That's not too fast. I thought I had 20 minutes. All right. So we didn't get to cover today randomness. We didn't get to cover today visibility of functions, unexpected Ethereum. There are many parts of smart contract security that we couldn't fit in this presentation. Maybe if I get with this rate, I could do that. But yeah, that's all I have today.
Excellent. Thank you very much.
Thank you. Thank you.
Before we move on to the questions from the audience, let me just check if there was one. I think there was a question about the re-entrance, right? Just refresh the question and answer screen. Yes, it's a question. Can we say re-entrance is a specialization of time of check, time of use attack, which is obviously a very common vulnerability in normal code, not just smart contracts?
That's a good question. Yeah, I think so. I think I can say yes to that. I need more time to think about this, but I think it's a yes.
It's just a standard kind of reference. Any questions from the audience?
Yeah, I mean, again, I understand Bitcoin, not Ethereum, but these attacks, I guess they're all specific to Ethereum and variations on Ethereum, are they not? Because
that's correct.
Something like Bitcoin, if you were in the pool, the time you've been in the pool is a factor, and that's part of the calculation of whether you get included in the next block, isn't it? Which I don't understand why Ethereum's removed that part of the calculation.
I'm not very familiar with Bitcoin mechanics under the hood.
Yeah, certainly the what you're calling gas, I guess in Bitcoin there would be the reward to the miner for a transaction fee, and obviously the ones with the big transaction fees get picked up quickly by miners who are looking for that. But if you have little or even no transaction fee, I think the time you've been sitting in the pool will then be included in the calculation, and eventually you get added to the next block. So I can't understand why Ethereum has like made these changes, like adding loops to the code, a possibility of a loop, and like removing time in the pool from the factory. So it seems like it's creating vulnerabilities in a later version than the reference client. So I don't understand what they're doing. I guess I'd have to read up on Ethereum.
The more functionality you have to a language, the more things you can do. And this is something that was lacking in Bitcoin. This is what they tried to do with Ethereum. And this is what they tried to do with the more advanced blockchains. In Ethereum, it's blockchain 1.0. And they don't have any logic, it's not Turing complete. They work with rewards, which is not the most efficient scheme. And this is why they actually have transaction costs as well. Because the block reward in Bitcoin, it is not enough. It's random. Whilst in Ethereum, they're mostly based in the rewards of the transactions. So basically the users pay the miners, and not the ecosystem itself, which happens in Bitcoin.
Yeah, there's both, isn't it? There's transaction fee and there's the reward
Yeah.
for running the block.
Yeah, in Bitcoin they add the transaction fee because they need it to operate the miners, because the reward is random. It is not certain that you're going to get some amount of money in some amount of time. It is, if you get the block, you're going to get the reward. And whilst in Ethereum doesn't work that way, it's a bit different. It's with transaction fees.
And I actually have a question with regards to integer overflow. Can I just go back to the integer one? Because obviously this is a very standard attack, right? Standard vulnerability, which is very common. And yeah, just the standard balance check missing. So we know what happens if you do it, for example, in a traditional programming language, right? But in Ethereum, you showed us a very interesting case here, right? When it's actually the value has gone over. But my question to you is, because in blockchain world, everything is hashed and signed, right? So how come the overflow, the value is now completely different due to the integer overflow? But isn't hash going to be different? Is it going to be caught at all?
Caught from what?
It will not. Is it going to be valid? Basically, that's my question.
Yeah.
So I don't think this transaction is going to be valid because the signature is not going to validate, right?
This is not Ethereum that's been transferred. It's the tokens of that blockchain. So yeah, it's not going to validate if you check it, but if you don't check it, it's not going to validate. I don't know if it makes sense, but yeah, you're overflowing, right? You have this huge number, and you don't have any buffer flows. You don't keep overflows. It's not exploitation like we regularly see. It's just changing the number and transferring an insane amount of funds. Again, this is not Ethereum, so it would be, it would be very weird if that was Ethereum.
I see. Okay.
That's another ERC20 token on top of Ethereum.
Right. Okay. Yeah. Understand. Thanks so much. Any more questions? Right. Okay. Thanks so much. For the last talk of the day,